Hello everyone. In this video we're going to be proving one of the characterizations of completeness in the real number line. It's called the nested interval property, and it's equivalent to our maybe initial definition of completeness in the real numbers. So we take R to be the complete ordered field, and so the word complete here, our initial characterization of it, and the one that we're going to use, is that if A is a subset of R and A is bounded above, this tells us that the least upper bound, or the supremum of A, is a real number. It exists. We have a supremum. Okay, so with that in mind, we want to prove this nested interval property. And let's take a look at what it's even telling us. It's saying that if I have a sequence of nested intervals, okay, IN, which is some closed intervals that are nested within each other. So to give a picture, right, let's imagine we have our real number line. And we take a sequence of intervals. So let's say my first interval, I1, goes closed intervals, right? So from A1 to B1, and that's, I1. And then the next interval is nested within it. Okay, so we have some A2 up until B2. Right, and dot, 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 all the way up until, maybe some arbitrary AN, dot, 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 dot. I put some dot, dot, dots there too. We have until BN, and it keeps going. So we're taking the infinite intersection of all these intervals. And the claim is that that's never empty. I can keep nesting closed intervals within each other, and I can never kind of squeeze in so much that I lose access to numbers, to any number on the line. It's another way to interpret the completeness. So I can always squeeze in until something, but it's never, so far that I lose the elements entirely. Okay, so, well, we want to prove this, and we're going to use the fact that R is a complete ordered field, so complete. We're going to use this characterization of completeness to show the nested interval property. So in other words, that this set right here, this infinite intersection of all the intervals, is non-empty. Okay, so let's take a look at a proof. Right? We're going to use the axiom of completeness to produce a single real number, x, that is in the infinite intersection. Okay? And the axiom of completeness states that every subset of R that is bounded above has a supremum. So we're going to use the supremum of some set is going to be that element in this set that makes it not empty. So we got to pick some A. What's our A? That's our set that's bounded above. Well, one way to think about it is that the set of all lower bounds of all these intervals is a subset of R and is bounded above by, well, all of the upper bounds of all these intervals. So we're going to work with that. So I'm going to say, consider A, which is the set of all ANs. We have it's a sequence, right? So it's a sequence of real numbers. We should note that A is bounded above by, well, any BN, right? Basically by definition. But including B1, if you want to just fix some number. And A is a subset of R. So this tells us that X, which we'll call the supremum of A, is a real number. And so we're going to claim, and we're going to show that x is in this infinite intersection. Start indexing at 1 if we want, whatever. Which proves our fact here, which is that it's not empty. So we used completeness here to show that this set of lower bounds of all those intervals, the supremum of that set is a real number. So we want to show that x is in this particular infinite intersection. Well, what does that mean if x is in this intersection? That means that for all n in n, x is less than or equal to bn, less than or greater than or equal to an, right? It's in the interval. You know, we can just write that x is an element of an bn, the closed interval, which is equivalent to x is greater than or equal to an, less than or equal to bn. Okay, well, so we have to show two things, right? Show x is greater than or equal to an. Well, this is clear, right? Because x is the supremum of a. So x is greater than equal to, so x is an upper bound for the set of all ans. Therefore, for some fixed n, we might want to fix n here. Imagine we're fixing n for something, right? But therefore, x is greater than or equal to an for all n in the natural numbers. And then the next thing we want to show is that x is smaller than or equal to bn. Again, for all n. Well, we have that bn is an upper bound for a for a for all n in n, right? No matter what the bn's, right? These bn's are always upper bounds to the set of all an's. But x is the least upper bound. And so we get, maybe I'll just put a therefore statement, right, that x is less than or equal to bn. So this is upper bound, this is also an upper bound, but we know that x is the least upper bound. So it must be less than or equal to all the bn's for all n in n. Therefore, we get that, we can kind of conclude that x is in an bn for all n in n. And so therefore we have that x is an element of the infinite intersection of all the ions. And so, of course, this infinite intersection is non-empty. We're done. We use this property that that ions they're nested in with each other. Essentially, kind of use it here, right, to say that all the bn's are upper bounds, right? So they're all nested. And otherwise, kind of just from the interpretation of it like this. Okay, that's all. Thanks for watching.